Okay, I am working on section 8.3 today, and this is about finding volume by using a cross-sectional area representation to build that volume. So you're looking at 4 examples here, and you can see different shapes of cross-sections are being utilized. For instance, we have a rectangle that will grow in width as these functions determine the distance across the plane here. So however thick that is, that it's more deep here than it was back here. So obviously that rectangle is going to grow as it moves from left to right. Same can be said over here. We see semicircles back near the origin, and you're looking at probably a 3D design here. Of course, I can kind of see the axes on here. Back here at the origin, you can see how it's very small, and then as we grow outward, our shapes are getting larger and larger, and the volume's growing. I've got rectangles, possibly even, the base is an equilateral triangle, and then they said they're squares, so these would be congruent sides, of course, there. And then this one's built off of isosceles right triangles, so it gets us a whole different shape. You're looking at kind of the net shape that would happen for that 3D object. So what we want to try to do is calculate out the volume when such figures are created by these cross-sectional pieces. And the general formula for the volume of solids with known cross-sectional pieces is this right here. Volume is the integral from a to b of a of x dx, where a of x represents the area of the known cross-section. So if you think about it, you're going to take area times the thickness, so a third dimension, and that's going to give you a 3D volume. Now, we also could have this written in terms of y. I could have a of y dy maybe integrated from c to d and be able to do cross-sectional volume that way as well. Sometimes it's oriented so that you have to do it with y's. So I'm going to walk you through. There's some easy ways to do this. It looks like it's going to be hard, but it's actually quite easy because you can see it's all based on the area of the cross-section. So what I need to know then are the geometric formulas for those cross-sectional pieces. So on this one, this is our x-axis, this is my y-axis, and the slices are running perpendicular to the x-axis. So I do want to work in terms of x's if that's the case. If it runs perpendicular to the y-axis, then I'm going to work in terms of y. We're working in terms of x's. So what I need to know is how wide is this at that point, or how wide at that point. And that will determine then the size of my square. And the distance from, this is f of x above, and this function is g of x. I would take my top function minus my bottom function to get the distance across the base. So this would be f minus g in length. And since this is a square, it's going to be also f minus g in its height. So I'm just making note I've got width and height figured out. And now I need to find the area of the square that I have written there. So we know that the area is equal to width times height, length times width, however you want to phrase it. And that's going to look like a of x, since I'm doing it with regards to x. I'm going to have f minus g times an f minus g. So I get an f minus g quantity squared. And that's the piece I need to know to come in and calculate out the volume. If I added up all the cross-sectional areas that were densely packed in here, you would have even more, right? In between all those voided areas, we'd have squares sitting in there. If we added up all those cross-sectional areas, we'd get the volume. How do we sum things in calculus? Well, we use an integral. So I'm going to go an integral from, and then I would have to find my oops, it's bouncing on me, I'm sorry. My integral, oh damn, whoops, sorry. Okay, I moved my sleeve because I think that's what was getting in the way. I'm going to call this, x equals a. I see it's really 0 there, but I'm just going to say let it be a, let this be b, so that we have our beginning and our ending point. So from a to b of the a of x dx. And in this case, that's going to be an a to b f minus g quantity squared dx. You could even put in x's in here, f of x, so that we know that our functions are expressed in terms of x. So square is pretty easy. Top minus bottom, quantity squared. What if we put in isosceles right triangles? And we do need to know how they are situated. These isosceles right triangles are situated on their leg, right? So it's a leg that's spanning the base, and I would have leg, leg. Since it's isosceles, these legs are going to be congruent. And this one is really kind of tilted. Let's call this the x-axis, this our y-axis. You can see that the upper function, once again, was f of x. The lower function is g of x. We're going to maintain that idea throughout these examples. Now, what I need to do is come up with the area of one of those triangles. So, what is the distance from top of the base to bottom of the base? It's running perpendicular to the x-axis. Well, that distance is going to be top minus bottom. Let's put f of x. F of x minus g of x. Since it's isosceles, then this will be f of x minus g of x as well. We've got a right angle there. Now, for the area of a triangle, well, the area formula for a triangle is 1/2 the base times the height, right? So I should be able to build any area I need just knowing my formulas, or perhaps I'm given a formula. And then that's going to be a of x is equal to, I need the 1/2, and then I have f of x minus g of x times f of x times g of x, because base and height were the same, so I really get a squaring there. If I added up all those little triangles, and they do get bigger as the distance between f and g grow, and it looks like they start getting smaller as f and g get closer together, all of that is determined by our functions and the distance between them. If I add them all up, I'm going to get the volume. Oh, don't know why it snaps back on me. So I get volume equals the integral from a to b again, those intersection points beginning and ending. We have a 1/2 f of x minus g of x quantity squared dx. And that I could pull that 1/2 out front, a to b, f of x dx, f of x minus g of x dx. Square that and dx. And there is our volume. Now, do I need to generate this each and every time they talk about a right isosceles triangle that is situated on its leg? No, I really don't need to, because I'm looking at the most general case right now. So if it is a right isosceles triangle situated on a leg, I can just immediately say it's going to be 1/2 the distance between the two functions, quantity squared. If it's a square, what's really up front is a 1 coefficient, right? And if you think about, you have a square, what happens if I cut that square into 2 pieces? I get a right isosceles triangle, don't I? And in that right isosceles triangle, I want to be able to highlight here. I would have half of a square, so it's half the square formula. So it makes sense, doesn't it? All right, next, equilateral triangles. What if we filled our space with equilateral triangles? This is too bad we aren't in school, because there's some nice models at school that you could view. But yeah, we don't have that option right now, do we? Let's call our upper function f of x, our lower function g of x. This is our x-axis, this is my y-axis. This would be x equals a, this would be x equals b. So we got our endpoints. And we want equilateral triangle, boom, boom, boom. Well, what do you remember about an equilateral triangle? All three sides are equal. All angles are 60 degrees. That's helpful, isn't it? And I know that I'm headed for this area formula that's 1/2 base times height. So I need to capture my base, don't I? And I also need to capture a height. We need the altitude of our triangle. So the distance across the base is this right here, right? That would be the base length, which of course is f minus g. And what I'm going to move that and put it down here, f minus g. And that's our base length. Now, if you recall, this is going to put us into a 30-60 right triangle so that I can calculate out what the height is. And this distance right here, from this point to this point, is 1/2 of f minus g, isn't it? And if that is the short leg, we can multiply by square root 3 and get to the long leg. So long leg, if you remember from your 30, 60, 90 right triangles, it will be root 3 times the short leg, 1/2 f minus g. So I now have my altitude, and I can come into this formula. So a of x is going to be root 3 over 2 times f minus g, and then the base is another f minus g. Oh my gosh, we're back to f minus g quantity squared. So really this is a takeoff of a square. F minus g quantity squared, right? That's kind of been the theme all along. There's a square, and now what portion of a square do I have? I got root 3 over 2 times that. So to get the cross-sectional area to add up, I'm going to say I have volume that's equal to root 3 over 2 integral a to b of f of x minus g of x quantity squared times the thickness of our slabs, which are dx. So another number to remember for an equilateral triangle, it's going to be root 3 over 2. All right, on to a semicircle. Semicircles, once again, this is going to be my, oops, that's not going to be my f. This is going to be my g of x function, my f of x function, my, looks like it intersects at x equals b here, starts at x equals a, and so on. Now, how far across is the semicircle? Well, it's top minus bottom, so the entire distance is f of x minus g of x. But we know the area formula for a circle, so circles have an area formula of what? Pi r squared. But we are semicircle, so what will that formula be? 1/2 pi r squared. Of course, we're working on area here. I didn't write that. So what do I need? I need to know the radius. Well, this is really a diameter, isn't it? This is the diameter across that full semicircle. Or this is the length of the base, right? Just like we've been talking about, base, base, base. So I need half of that. So radius equals 1/2 of the diameter. 1/2 of f of x minus g of x. And now I can go in and calculate the area of our semicircle. 1/2 pi, and let's insert our r, which is 1/2 f of x minus g of x. And we need all that r to be squared, including the half, right? So where does that take us? I'm going to have pi over 2, let's just simplify that lead coefficient, times a 1/4, squaring the half there, and then that's going to leave me an f minus g, or an f of x minus g of x quantity squared. All right, one last simplification. I am going to get, for a semicircle, a pi over 8 coefficient times f of x minus g of x quantity squared. So you can see that everything that we're doing essentially is built off of the area of a square cross-sectional piece. And the only thing that we're adjusting is that lead coefficient. And it makes all the difference in the world. So if you can memorize a few things, you don't have to do the calculating or the discovery of coming in with those areas. What I'm hitting here are the most commonly used ones on the AP exam. And I would suspect that you will definitely, we need an integral, a to b. I would suspect that you will have a cross-sectional volume defined somewhere in the test. Used to always be free response. I would say now it almost tends more to be embedded in the multiple choice. You can almost count on a volume in free response, and that's not so much the case anymore. So the integral from a to b, pi over 8 out front, area of the cross-sectional piece squared, dx. So down below it says, what do you notice about the integral defined formulas for finding the volume of the solids with certain cross-sectional pieces? It's always some lead coefficient times the integral, a to b if we're working in x's, let's say, of f of x minus g of x, quantity squared, dx. And that is our volume. We recall that this was really the area of the square. Also kind of remember that this is top function minus bottom function to get that difference between the two functions, that span across the base, this distance here, top minus bottom. So I hope this is making sense. And then I think we go into this problem with, I've seen this shape so many times. Find the volume of the solids formed when the cross sections are shapes indicated below. The cross sections are perpendicular to the x-axis. So that means that they're going to be running this direction, which then I'm going to take top function. Which is the top function? I gotta believe it's gonna be sine of pi x minus x cubed minus 4x. And so to get the distance between them, we're going to go top minus bottom, sine minus the cubic. Now, we're going to do equilaterals, we're going to do semicircles. Isosceles right triangles, we're going to say, you know what, I want to put this one on the hypotenuse, so that the hypotenuse is spanning the base. We did not do this in our notes, so that one I'm definitely going to show you how to get that coefficient number. We got squares, we got rectangles. This is another one that we need to hit, is what happens on those rectangles. All right. Yeah, so those will be good. Let's run through these examples. So cross sections that are equilateral triangles. Well, if I look back, equilateral triangles had a root 3/2 coefficient. So I'm going to use that. Volume is equal to the integral from a to b of a of x, the area of the cross section, times the thickness of it. It's good to recall what the base formula is. And that's why I'm repeating it, because sometimes the AP tells you the area of the cross-sectional piece is blah, blah, blah. And people are so used to going top minus bottom that they don't know what to do with it. But yet, they actually gave it to you if they say the area is. Now, what I need to know is where these intersect. You know what? I think we're going to assume 2, and we're going to assume 0. 2 times pi would be 0. 2 would be 8. 8 minus 8 is 0. So yes, definitely this point is 2, 0. And this point is also 0, 0. We could validate both those going in. Now, let's go. Volume. Since we're working with an equilateral triangle, I'm just going to go straight into root 3/2. The integral from 0 to 2, that's our a to b. And I need to go top function, sine of pi x, minus bottom function. Needs an extra parenthesis because of the distributing of this particular negative, right? So get that in there. And then it's all of, or it's that difference squared dx. I don't have a number for you. You could put it in your calculator if you wanted to. Cross sections are semicircles. Okay, what's the formula for semicircles? It is a pi/8 coefficient. So I'm going to get volume equals pi/8. See, these are easy once you get rolling on them. Integral from 0 to 2. I need the span across the base squared. So my span is top function minus bottom function. Extra parenthesis required. All of this squared dx. Cross-sectional isosceles right triangles on the hypotenuse. Okay, this is where it gets a little bit tricky. We did the one that looked like this, right? And we figured out that this had a 1/2 relationship. If I didn't draw that very well. If I am on the hypotenuse, then my right triangle is going to look like this, with the right angle there, equal legs here, and here is our hypotenuse spanning the base. So this is creating our base length. Well, I think I'm going to take the fastest way and show you. It's not going to be real accurate, but it's the best I can think of. I have 1, 2, 3, 4 equal right isosceles triangles configured with the hypotenuse as an outside segment of the square, or the distance across the base. And obviously this blue area represents, let's do blue area, represents 1/4 of a square. So 1/4 is going to be my multiplier. 1/4 integral from, what were we spanning? 0 to 2. Top function, sine pi x, minus parenthesis, what was it, x cubed? X cubed minus 4x, quantity squared, dx. Wasn't so bad, was it? Maybe you'll remember these pictures to remember the fourth on this one, half on this one, because this one's half of a square. Cross sections are squares. Well, that means that my coefficient is a 1, because I've got the full square, so volume equals the integral from 0 to 2. I just need the distance across the base. Squared dx. That one's done. All right, now for the last two that are new, what about if it was a rectangle? In the rectangle, they will usually describe what the relationship is between the base and the height. So it says whose height is twice the length of the base. So the height is equal to 2 times the base length. So if my base was here, then the rectangle is going to be taller. Let's make it really taller. Taller than it is wide, right? So this would be the base, and this height would equal 2 times the base. How do I capture the base? Top function minus bottom function. Always comes back to that if I'm running perpendicular to the x-axis with my slabs. And in this one we are. So we are going to have f, no, I don't want to go f of x. I want to go sine pi x minus parentheses x cubed minus 4x. That's our distance across the base. And then, of course, the height is going to be 2 times that. So my area of the rectangle, of course, is length times width, or base times height. My base is going to be sine pi x minus x cubed minus 4x. There's our base. And then let's multiply it by our height. And that height is going to be 2 times, and then I got to write all that other stuff, sine pi x minus parentheses x cubed minus 4x. Boom. Do I have an extra parenthesis? Nope, I'm okay. Now, what does that boil down to? Well, that boils down to I could bring my 2 out front, and then I notice that I've got top minus bottom quantity squared. Whew! Because this multiplied by the exact same, right? That gives us that squaring. Now, taking it into a volume function. We'll put a 2 out front, but that's only because of the design for this particular rectangle. From 0 to 2, sine pi x minus x cubed minus 4x quantity squared dx. F, cross sections of the rectangle whose height is 1/3 the length of the base. So you can kind of imagine, actually we've got a long skinny one, don't we? It's 1/3 of the base. So this will be 1/3 the base. This is the base. So hopefully you kind of see by now, I'm not going to go through all of the detailed information here, but I can pick up that I'm going to have a 1/3 base times base. So 0 to 2, base times base. And to get that base, it's the distance across. So top minus bottom quantity squared dx. Okay? There's some very good examples of things that you will encounter on the worksheet. You may encounter the y's where it's perpendicular, if it's running perpendicular, if my function is, I don't know, I don't have a very good function here. I need a, I can't even think, guys, it's late. Let's say we had some function there and then maybe some slab like that, so that we get a base going of here of our function. And then what I need to do is position, maybe I'm putting semicircles in here. So they'd run in like this, right? And I have all these semicircles spanning that. And in this case, I'm going to want to go right function, which I'll call f of y, and then left function, which I'm going to call g of y. I'm going to have an intersection point of d and an intersection point of c. And that will give me a function that goes c to d of f of y minus g of y right minus left quantity squared dy. So it's really, you know, it's just operates the very same idea. This was right minus left, just like when you were calculating area out. Same idea, right minus left quantity squared. And if this one, if I was using semicircles, then I would know that my prefix or my coefficient was pi over 8. Okay? Homework is the worksheet here, so good luck. Finish that up and upload that to Schoology.